Welcome back to the workshop. Today we are doing a complete teardown and analysis of a 60 kilowatt-hour BYD Blade Battery pack taken from a BYD Atto 3. This pack weighs almost 420 kilograms and looks more like a piece of heavy armor plating than a battery. Many of you asked me to open it up and show exactly what's inside, how the cells are arranged, how the cooling works, and whether we can actually remove individual cells. So today we will go through the entire disassembly process step by step. First and most importantly, safety. This battery contains 60 kilowatt-hours of energy at around 400 volts. Before touching anything, we fully discharge the pack down to under 5% state of charge. Then we connect a controlled bleed resistor and slowly drain the remaining energy over several hours. Only after that do we remove the orange high-voltage connectors. We work with insulated tools, rubber gloves, and proper high-voltage PPE because one mistake with this much power can be extremely dangerous. Now we start the mechanical disassembly. More than 100 bolts secure the heavy aluminum top cover, along with a continuous bead of structural adhesive around the entire perimeter. We apply heat to soften the adhesive and remove the bolts in a careful sequence to prevent warping. After everything is loose, we finally lift the lid. Look at this. The interior of the blade battery is very impressive. The long blade cells are arranged transversely, running crossways across the entire width of the pack. There are no separate modules at all. This is a true cell-to-pack design. The cells are packed extremely tightly with almost no wasted space. Right on top of the cells, you can see the cooling system. Refrigerant lines run back and forth in a serpentine pattern directly above the cells. This direct cooling is one of the strong points of the blade battery. It helps maintain optimal temperature during both fast charging and high discharge. Running along the top is the battery management system board. It spans almost the full length of the pack. You can see it is spot welded in place and has voltage and temperature sensing connections on both ends of every cell. Everything is properly insulated with mica sheets to prevent any risk of short circuits. Now comes the difficult part. We're trying to lift the cooling assembly and bus bars. It's not coming up easily. The cells are bonded extremely strongly to the bottom tray and to the cooling plates using industrial-grade structural adhesive. This glue is incredibly tough. Even with heat and mechanical leverage, it's very hard to separate. This is the biggest limitation of the BYD Blade Battery. The cells are glued so firmly that removing even a single cell without damaging the cooling system or the structural integrity of the pack is almost impossible. This design makes the battery very strong and safe, but almost impossible to repair at the cell level. BYD clearly designed this pack for complete replacement rather than individual cell service. Let's look closer at the bus bars. They are made of heavy-duty aluminum and copper. Every single connection is spot welded. The construction is very robust and designed to handle high current without issues. However, if you ever want to rewire this pack for a different project or different voltage configuration, you will have to cut through every one of these welds. After a lot of careful work and patience, we managed to pry out one complete cell. It weighs approximately 2.4 kilograms. Each cell has a nominal voltage of around 3.25 volts and a capacity in the range of 135 to 202 ampere-hours, depending on the exact variant. When you multiply that across all the cells in the pack, you get the total 60 kilowatt-hour capacity. The chemistry inside is lithium iron phosphate, or LFP. This chemistry is known for being very stable, long-lasting, and resistant to thermal runaway. BYD didn't create a brand new chemistry. What they did was change the cell geometry, making them long and thin like blades, and integrating them directly into a structural pack. This smart packaging allowed them to achieve good energy density and excellent safety at a lower cost compared to nickel-based batteries. Looking at the rest of the pack, the aluminum cooling plates have internal channels designed to distribute coolant evenly. The entire battery housing is also a load-bearing structural component of the vehicle chassis. This improves crash safety and torsional rigidity, but again adds to the difficulty of repair. Real talk, the Blade Battery is brilliant engineering. It is cheaper to manufacture, very safe, structurally strong, and gives competitive range for an LFP pack. It shows that you don't always need exotic nickel chemistries if you optimize the design properly. However, the downside is clear: repairability is poor. If one cell fails in real-world use, most service centers will simply replace the entire expensive pack. After several hours of disassembly, here we are. All the cells, bus bars, cooling plates, and BMS are laid out. The empty housing now looks surprisingly light compared to when it was fully assembled. This pack truly represents where the EV industry is heading. Higher integration, better efficiency, lower cost, but with trade-offs in serviceability and end-of-life recycling. This was part 1 of the BYD Atto 3 blade battery teardown, full disassembly and detailed analysis. In part 2, we will try to cut the bus bars, rewire the pack, and see if we can make it usable for other projects like off-grid storage or EV conversions. If you like this detailed teardown, please hit the like button and subscribe for part 2. Let me know in the comments. Do you think the advantages of this design are worth the repairability issues? Thanks for watching. See you in the next one.